astronomers have discovered a staggering clutch of 15 new giant radio galaxies within the Sculptor field view of Australia's Square Kilometre Array Pathfinder ASKAP telescope. This is a big deal because giant radio galaxies are the largest single objects in the known universe, each wider than 2.3 million light-years across. These new examples range in size from 3.7 million light-years to a staggering 12.4 million light-years wide. For context, the Milky Way is around 105,700 light-years wide. That means our galaxy would fit across the largest of these new giant radio galaxies. Designated ASKAP J01072347 over 117 times. ASKAP J01072347, located around 1.5 billion light-years away, is also remarkable because it features two sets of radio lobes, one inside the other. The inner lobes are bright and short, while the outer lobes are faint and elongated. This nesting doll-like structure could hint at how giant radio galaxies get so big. Giant radio galaxies are the biggest single objects in the universe. They are similar in size to the whole local group, which includes the Milky Way, Andromeda, and lots of dwarf galaxies. A giant radio galaxy is a massive elliptical galaxy that has a supermassive black hole at its heart. When these black holes are feeding on surrounding matter, creating a region called an active galactic nucleus, AGN, they blast out powerful jets of matter at near-light speeds. All large galaxies are thought to have supermassive black holes at their centers, and many of these are feeding or accreting matter and thus sit in AGNs while exhibiting jet activity. What sets giant radio galaxies apart is the fact that their jets stretch out for 2.3 million to 15.3 million light-years, creating vast twin radio wave-emitting lobes around these galaxies at the shock front of these jets. Black holes are feeding, and powerful radio jets are seen to emerge from near the black hole. Other times, the supermassive black hole is inactive, so we see no jets, and the lobes that formed around the head of the jet slowly fade. That is, the researcher added, unless the jets and lobes are mergers between galaxies are thought to play a role in restarting supermassive black hole activity, thus recharging these jets and creating a second brighter set of inner lobes. To investigate this phenomenon as well as fading radio lobes, Korobulski explained that three things are necessary: high sensitivity, good angular resolution, and relatively low observing frequency. ASKAP, a 6-kilometer diameter radio interferometer array comprising 36 telescopes in Western Australia, provides high-resolution wide-field radio images and thus fits that bill nicely. Because ASKAP is equipped with novel wide-field receivers, checkerboard phased array feeds that look like a chessboard, we can carry out huge sky surveys. In each observation, we see an area of 30 square degrees, while previous radio interferometers would see around 1 square degree. So, each image produced by ASKAP is a treasure trove. The ASKAP data used was centered around the starburst galaxy NGC 253, or the Sculptor galaxy, located around 8 million light-years away, creating the deepest ASKAP field yet, the Sculptor field. While inspecting this deep ASKAP field, I found an unusual number of giant radio galaxies, not only physically very large, but also large in terms of their angular sizes. The latter, together with the depth of the field, makes it possible to study these giant radio galaxies in great detail, in particular their morphology, symmetry, and ages. The ASKAP data could help to get to the bottom of giant radio galaxy growth, because whereas the old lobes of these huge galaxies are so big, diffuse, and faint that they are generally not detectable in shallow surveys, the ASKAP surveys are deep enough to see these fainter structures. ASKAP J01072347 is a prime example of this form of galactic archaeology, and it could soon be joined by many more double-lobed giant radio galaxies, helping to crack the mystery of these vast cosmic structures.